So recall that when we're looking at integration, it's just the inverse of differentiation. In other words, what we're saying is when we're taking the antiderivative and we're taking the integral and doing integration, those are the exact same thing that we're trying to do. However, we're not always going to be given some sort of limits of integration. Sometimes we'll be given an integral that doesn't have any bounds and a function inside of there, and we'll just be trying to anti-differentiate. So here, we're just going to find the most general antiderivative. So if you have no integration bounds, that is called an indefinite integral. So last section we looked at definite integrals. Now we're looking at indefinite integrals. And the way we're going to find this is we're just going to take the antiderivative of whatever the function is. So if we have x squared, the antiderivative of this is going to be equal to x to the third over 3. So we added 1 to the power divided by the new power plus c. Again, because this is the most general form of the antiderivative, we want to make sure that we add that constant on there. And then recall, if you take the derivative of this, that would be 3 times a third, which would just be 1, and then x to the 3 minus 1, or squared, so it would just be x squared, and the derivative of this would be 0. So that works out. So whenever we're doing indefinite integrals, the answer we have is going to be some sort of function, whereas when we do definite integrals, that's when we plug things in, we have integration bounds, and we find a specific number. Alright, so say we wanted to do a few more examples of indefinite integrals. So if we've got the integral of 10x to the fourth minus 2 secant squared x dx, the antiderivative of this will be found by taking the antiderivative of each of the individual pieces. So this would be 10 times the integral of x to the fourth dx minus 2 times the integral of secant squared x dx. Now we take the antiderivative of each of these, so we'd get 10 times x to the fifth over 5 minus 2 times the antiderivative of secant squared, which is tangent of x, plus c. And then, of course, we would simplify things with the 10 and the 5, and we'll get 2x to the fifth minus 2 tangent of x plus c. So this is the most general form of the antiderivative, and this also would just be what the indefinite integral was. When we get to this next example, this is a little bit trickier. So we've got some sort of fraction here, but we don't have a quotient rule for antiderivatives. Because that looks almost like what might have happened to get here. So what we're going to do is we're going to simplify this by rewriting it in some way. So this is the same as being the cosine of t divided by the sine of t times the sine of t dt. Now, if you look at cosine over sine, this is cotangent, and if you look at 1 over sine, this is cosecant. And so this integral is the same as the integral of cotangent of t times cosecant of t dt. And so that means that our antiderivative here is negative cosecant of t plus c. So This is a little bit more of an obscure one, so it'll be helpful to kind of remember what our rule is for cosecant there, and then how we get negative. So if you're not sure where this is coming from, go back and look at those notes we had on trig derivatives, and that'll help you out. Alright, now this was a pretty complicated looking function, or that we wanted to take the antiderivative of, and we got lucky that we could kind of use some identities and break it into something that we could, actually use. But we're not always going to be that lucky. Suppose we're asked to find the antiderivative of this function here. 12x plus 4 divided by 6x squared plus 4x plus 1, whole thing squared, dx. Because we can't just simplify this, and it doesn't match any of our basic integral forms we've got so far, we're going to have to do something a little bit tricky in order to be able to evaluate it. And it won't be able to evaluate it, we won't be able to evaluate it quite as written. So in order to do this integral and evaluate it, we're going to have to use a certain type of substitution that will transform it into some known basic form. And this process is going to be called U substitution. So say we want to do the process for U substitution. There will be 4 main steps. Step 1 will be to start with the problem in terms of x. So we start with problem in terms of x. Now to get from this part of the process to the next part, we are going to make a substitution for x. In other words, we want to be able to get x completely out of the problem and write it in some other variable. And so what we'll do is we will let u equal some expression involving x. Now at this point we get to the second stage of the problem, whereas we now have the problem is in terms of the variable u. So u will become a new variable we have. And one of the hardest parts about u substitution is making sure we pick this expression correctly. Now, how we're going to pick our expression is we want something that will allow us to use the basic antiderivatives we know with u. So we will evaluate by matching our basic antiderivatives that we already have. Now, once you've evaluated this, you've now taken your antiderivative, you get to the next stage. And the next stage is you now have a solution with u as the variable. But the problem didn't start with u. It started with x. So what we'll do next is we will replace u with the original expression in terms of x. And then finally, what that means is that the fourth stage of this problem is we will finally have an answer with x. And so we'll have our final solution. So these 4 steps are going to be our process for performing u substitution. And they'll help us deal with less kind antiderivatives such as this one. So the logic here and the reasoning behind this is you can think of this as being the reverse of the chain rule. In general, this works whenever we have an integral that could be written in the form integral of f of g of x times g prime of x dx, which we could also think of as being the derivative of the outside with the inside plugged in times the derivative of the inside. So here is our substitution rule. If u is equal to g of x, if g of x is some differentiable function, then the integral of f of g of x times g prime of x dx will be the same as the integral of f of u du. Now this is a very important thing that just happened here at the end. Whenever you have this dx, what that's telling you is that your variable is x and you want to take your antiderivative with x being the thing you're treating as your variable. However, when we replace this with u, we're going to have to replace this dx somehow with a du. And so as we go through the next couple of problems, we'll see how exactly that pans out. So say we wanted to look at the exact example we had from before. So stage 1 was starting with our problem x. From here, we want to go ahead and figure out what u should be in order for us to try to evaluate this. Now, what could be very useful for you is to make this down here our u. So if we let u be equal to 6x squared, 4x plus 1, what we will do is we'll take the derivative on both sides of this expression. So we'll get du dx on the left-hand side, and on the right-hand side we'll get the derivative of this with respect to x, which will be 12x plus 4. Now we would like to replace this dx so that we have du available to us. So we want to get dx in terms of du. So what we'll do is we'll multiply over, so we'll get du equals 12x plus 4 times dx, and then we will divide on the other side. So we'll get du over 12x plus 4 equals dx. And now this will be what we need in order to plug back into here and write this in terms of u. So this will be then the same as the integral of 12x plus 4 divided by, we said that 6x squared plus 4x plus 1 was going to be u, so this will just be u squared. And then we said that dx would be replaced by this du over 12x plus 4. So times du over 12x plus 4. And what we can see at this point is that the 12x plus 4's should cancel. And we'll end up with the integral of 1 over u squared du, which is the same as the integral of u to the negative 2 du. Now at this point, this is something we can integrate. We've got du, so we know we're using u's, and we've gotten rid of all the x's. So now the antiderivative of this will be negative u to the negative first power plus c, or in other words, it'll be negative 1 over u plus c. Now at this point, we've taken the antiderivative, and now we need to go ahead and plug what we had for u back in, so that way everything's in terms of x. So this will end up being negative 1 over 6x squared plus 4x plus 1 plus c. So again, we want to make sure we go through our whole process. We want to pick a value for u that is going to drastically simplify the problem. We will then take the derivative of it, flip things around so that way we can solve for dx and replace it with something in terms of du. If we need to do some cancellation to get rid of the rest of the x's, hopefully what we've picked will be good enough to do that, and then we can go from there. Now, you might be sitting at home wondering, how did I pick 6x squared plus 4x plus 1? Well, the reason I picked 6x squared plus 4x plus 1 is when I take a look at this function that I want the antiderivative of, the most complicated thing here is having some function being squared. I don't know how I would cancel this otherwise, and so that was a clue to me that this would be where I want to start and focus on. Taking a look at example 5, say we want to pick a value for u here. Again, we want to pick something that on its own could be very complicated unless we took and simplified part of that. So take a minute, or take a few seconds, maybe pause here, and see if you can figure out what u should be for this problem. Think you got your guess? Great. So here, this expression is being raised to the third power. So that makes me think that 3x squared plus 5 might be a good choice for u. So if u equals 3x squared plus 5, what I'll next do is take the derivative on both sides. So we'll get du dx on the left, so the derivative of u with respect to x. On the right, we'll get 6x. So if we try to solve to get dx by itself, we'll have that du equals 6x dx. And then we'll divide over to get du over 6x equals dx. Now, I've seen a lot of students over the years, and I've been one myself, that'll do this last part of the process a little too quickly. And they'll end up kind of flipping du and dx somehow and getting a wrong answer that way. So do take your time when you're doing this part. Make sure you're multiplying the dx over and then dividing what the other thing is and making sure you have everything where it needs to be. Okay, so using u and dx to replace things here, we have this is equal to the integral of x times, we said 3x squared plus 5 was u, so x times u to the fifth, not to the fifth, to the third, u to the third times dx, which we said would be du over 6x. Now again, x and x will cancel. Now if you don't get all of your x's to cancel, you should pick something different for u or double check your work, because you'll be looking at things where the x's should go away. So now we get the integral of u to the third over 6 du. And at this point, we just have to take the antiderivative. So this will be 1 over 6 times u to the fourth over 4 plus c, which will be u to the fourth over 24 plus c. But again, we still have things in terms of u. We would like to use x instead. So this will then become 3x squared plus 5 to the fourth over 24 plus c. Okay, so again, we want to make sure we're understanding this idea of how we're going to deal with the substitution. We often know which part of the integrand, we're often going to have that be the biggest part of a problem, right? Figuring out what to have u represent. Now, these suggestions are going to often, but not always, work. So if the integrand involves a function raised to a power, we're going to let u be equal to what's being raised to that power. So what it's being raised to a power. So here we had 3x squared plus 5 to the third, so we picked 3x squared plus 5. Here we had 6x squared plus 4x plus 1 squared, so we took what was being squared and made that u. If we have some sort of radical or square root, we're going to let u be what's under the radical. Remember that a radical is really just a different power of something, so these two are very, very similar. However, whatever you pick for u, some form of its derivative should be also in the integral. What do I mean by that? Well, when we looked at making 6x squared plus 4x plus 1 our thing that we picked for u, the antiderivative would be, the derivative of it would be 12x plus 4, which is in the problem, which is nice because then we got it to cancel out. When we looked at x times 3x squared plus 5 to the third, 3x squared plus 5's derivative was 6x. And while the whole 6x was not in the integral that we were trying to simplify, we still needed to make sure x went away. Now, one big thing to note is that this is not always an exact science, but these are things that can help us out. So the process for determining what to let u be is going to involve some trial and error. And if this doesn't work, keep picking alternatives until you get something that does. Alright, so with this knowledge, I'm going to challenge you to try the next 5 problems. So we've got 5 integrals here. And I would like you to pause the video right now and, given these instructions, see what you can do to find all 5 of these indefinite integrals. Are you back? That was fast. Cool. So, say we want to go ahead and find the antiderivative of this. We want to find the indefinite integral. We're going to want to use u substitution because this is a little bit of a crazy thing for us. And we have the cosine of something. Now, in general, we know how to take the antiderivative of cosine of x, but we might not know how to do it of cosine with some stuff in it. So what we're going to do is the thing that's inside the cosine is what we're going to make our u. So u will equal z to the 4th plus 2. Now at this point we want to take the derivative of both sides. So since we're taking the derivative with respect to z, z is our variable, we'll have du dz on the left. On the right, we'll have the derivative of this, which will be 4z cubed. And now since dz is our thing in the problem, we'd like to solve for that. So we'll multiply dz over, we'll get du equals 4z to the third dz. And then from there, we'll go ahead and divide, and so we'll get du over 4z to the third equals dz. So now when we go to do our substitution, we'll have z cubed times the cosine of u, because we now have made z to the 4th plus 2 our u, times dz, which we're replacing with du over 4z cubed. Again, these z cubes will cancel. And so what we'll be left with is 1/4 times the integral of cosine of u du. And so here the antiderivative will be 1/4 sine of u plus c, but we need to put our u back, and so we'll end up with 1/4 sine of z to the 4th plus 2 plus c. So z is back in the problem now, and we have our final answer. All right, what about the next one? Well, again, the thing under the radical is probably the thing we should make be our u. So we'll have that u will equal 2x plus 1. That means that du dx will equal 2. And that means du will equal 2 dx, and that du over 2 will equal dx. So that means by doing our substitution, we have the integral of the square root of u times du over 2, which can be written as the integral of u to the 1/2 times du over 2. And the antiderivative of this will be 1/2, for the 1/2 here, times u to the 3/2 divided by 3/2 plus c. This means that we'll have 1/2 times 2/3 times u to the 3/2 plus c. The 2's will cancel, and that'll give us u to the 3/2 over 3 plus c. And then last but not least, we don't want to keep things in u. We want to go back to x. So this will be 2x plus 1 to the 3/2 over 3 plus c. Who's having fun? I'm having fun. This is a good time. All right. Next, let's look at the integral of y divided by the square root of 1 minus 4y squared. So again, we've got a radical. Usually our thing that we're going to want to focus on here is what's under the radical. So u will equal 1 minus 4y squared, and du dy will equal negative 8y. Now, why did I do dy? Again, y is our variable, so we're taking the derivative on the left and on the right with respect to the variable y. This means that du will equal negative 8y dy, and that means that we'll get that du over negative 8y equals dy. So we'll take this and rewrite it as the integral of y over the square root of u times du over negative 8y. Again, just make sure you know where everything's coming from. The u comes from the fact that we said 1 minus 4y squared was going to replace it. The du over negative 8y comes from us replacing the dy. And so now the y here and the y here will cancel, and we'll get the square root of du over the integral of du divided by the square root of u, and then times negative 1/8. Could have put the negative 1/8 out front if we wanted to, but this is the same as negative 1/8 times the integral of u to the negative 1/2 du, which means taking the antiderivative, we will get negative 1/8 times u to the 1/2 divided by 1/2, or negative 1/8 times 2 over 1 times the square root of u. Sorry, this should be plus c, and this should be plus c. The 2 and the 8 will reduce. This is a 1, this is a 4. and we still need to replace our u. So we will end up with negative square root of 1 minus 4y squared over 4 plus c. All right, 2 more of these examples. Then we'll talk about something else that's kind of fun. Again, we don't necessarily know how to find the antiderivative of cosine if we've got 5x in it. Normally we just are used to doing this with x, so we can use u substitution here as well. And hopefully it'll match what your intuition is if you've seen examples taking derivatives of something like this. So here we'll have u equals 5x, and we'll get that du dx will be equal to 5. This, of course, means that du will equal 5 dx, and that du over 5 will equal dx. Okay, so what does that mean? It means that we can take and rewrite this as the integral of cosine of u times du over 5, which will be the same as sine of u over 5 plus c. And this will just be, once we replace the u, the sine of 5x over 5 plus c. Okay, one more indefinite one, and then we'll talk about how we do substitution with definite integrals. All right, so we've got this function for us right here, and this will be a little bit tricky. So normally we're going to choose the thing under the square root as u. So u is going to equal x plus 3. If u equals x plus 3, then du dx will equal 1. And that means that du will equal dx. Okay, great. So that means this is the integral of x times the square root of u du. But that's a problem because we aren't allowed to have any x's. So we need to replace this with something involving u. Well, what we'll do is if we know that u equals x plus 3, then we'll treat this the same as u minus 3 equals x. These are the exact same equation, we just have the 3 moved over. So, but logically these say the same thing. So that means we have the integral of u minus 3 times the square root of u du. And of course we can think of the square root of u as being u to the 1/2, so this is the integral of u to the 3/2 minus 3u to the 1/2 du at the end of the day. And so the antiderivative of this would be u to the 5/2 divided by 5/2 minus 3u to the 3/2 divided by 3/2 plus c. This would mean that we had 2/5 u to the 5/2 minus 2u to the 3/2 plus c. And by the time we've replaced u equals x plus 3, we'll end up getting 2/5 times x plus 3 to the 5/2 minus 2 times x plus 3 to the 5/2 plus c. So watch out for some of these. If you can't find something where the derivative will get rid of the other part with x, look to see if there's a way to rewrite the expression with u to solve for x in terms of u. And that'll be another method you want to keep in your back pocket. Okay, so let's say we want to go ahead and deal with definite integrals. So remember, definite integrals are things where we have bounds on either end. How we can do this is one of two ways. The first way is we can go and evaluate the indefinite integral first and then plug in the limits of integration. So we can go through the entire process and then plug in the original numbers and be good to go. The other thing we can do, if we don't like doing this step where we go from u back to x, is we could change our limits of integration when we change our variable. And then we don't have to worry about that other part. This is usually the method that confuses people the least. So this is the typically less confusing method. Now, I want to be clear, you do not have to use both of these. You can just learn this one and do everything we've done up until this point and then plug in the bounds and everything will be fine. Some people will find this to be better, and if you ever get into a scenario where you start dealing with polar coordinates, say you get into a Calc 3, this will become nicer to understand and deal with. I'm going to do these last two problems here, the first one using this first method and the second one using the other method, and you can evaluate for yourself which you think is better. So this will be using method 1. We want to evaluate the integral from 1 to 2 of dx over 3 minus 5x quantity squared. So here u will equal 3 minus 5x because that's the thing being squared. So du dx will equal negative 5. That means du will equal negative 5 dx, and du over negative 5 will equal dx. That means that we're taking the integral of 1 over u squared times du over negative 5. Or in other words, this will be negative 1/5 times the integral of u to the negative 2 du. This will then become negative 1/5 times u to the negative 1st over negative 1 plus c, or just 1 over 5u plus c. This, of course, means that we would go ahead and change back, so we would get 1 over 5 times 3 minus 5x plus c, and at this point we then have to go ahead and plug in our limits of integration. Now, what you might have noticed from before is that when you do this and you have the plus c, the c should cancel. So remember, this will be us plugging in 2 for x and then subtracting what we get when we plug in 1 for x. So this then becomes 1 over 5 times 3 minus 5 times 2 plus c minus 1 over 5 times 3 minus 5 times 1 plus c. By the time we've distributed this negative, the c portions are going to cancel. And what we'll get is 3 minus 5 times 2. 3 minus 5 times 2 will be negative 7. And so we'll get negative 1 over 35 minus 5 times 3 minus 5 times 1, which will be negative 10. So we'll get this as our answer. And so negative 1 over 35 plus 1 over 10. By the time we've simplified, will give us 1 over 14 as a final answer. Now this is method 1. The other method, we'll use method 2 here, will involve changing what these bounds are. So we're going to go from 0 to 1 of 3t minus 1 to the power 4 dt. So we'll let u equal 3t minus 1. That means that du dt will equal 3, and du will equal 3 dt, and du over 3 will equal dt. Now some people might wonder, well, if we change 0 and 1 to be in terms of this, what we have here, won't we not have to substitute back? And the answer is, yeah, that's true. So we're going to plug in and figure out if we're going to change our bounds by saying if t is this, then we get this, and if t is this, then we get this for u. Change the limits of integration. So if we want to change those limits, if we let t equal 1, then we'll have u will equal 3 times 1 minus 1, which will be 2. And if we let t equal 0, then we'll get that u equals 3 times 0 minus 1, or just negative 1. So this means that we have the integral from negative 1 to 2 of u to the 4th times du over 3. So again, just so we know where everything's coming from, we said that 0 would become negative 1 in terms of u. We said that 1 would become 2 in terms of u. We said that 3t minus 1 is u, so we've replaced that there. And then dt is du over 3. Taking the antiderivative then will give us 1/3 times u to the 5th over 5. And this is what we would want to evaluate from negative 1 to 2. I'm going to simplify that a little bit. We'll have it be u to the 5th over 15 evaluated from negative 1 to 2. And so that means we'll have 1 over 15 times 2 to the 5th minus 1 over 15 times negative 1 to the 5th. And so that will give us 32 over 15 minus negative 1 over 15. So for minusing a negative, that's adding. And so we end up with a grand total of 33 over 15. Now, if you want a little bit of extra practice, you can use method 2 on the first problem and method 1 on the second problem. And either way you go, you'll end up with the exact same answer. You do not have to memorize both. You might find one easier than the other. I'm personally a bigger fan of method 1, but again, to each their own. But that is how you will go ahead and use this substitution method with your definite integrals.